Now before we go ahead and look at the cosine function, let's look at both the sine and the cosine in terms of a Taylor approximation. So we have the sine function here. We can look at a first order approximation as a straight line. So this is a line y equals x, and you can see here the approximation is quite good for small values of x. So it means that for small values of x, you could say that sine x is approximately equal to x. Now we also have added in the second term, which is the minus x to the power of 3 upon 3 factorial. So that approximation looks like this here, and you can see it's a better approximation over a wider range. And we've also gone up to the next approximation, which is the x to the 5 upon 5. So you can see here that our approximation is actually really quite good up until about 90 degrees, and then it tails off, and again for minus 90. So it really tells us that our approximation that we have used for the sine function, which is the x minus x to the 3 upon 3 factorial plus x to the 5 upon 5 factorial, is going to be good up to about 90 degrees. But that's all we really need, because for any angle greater than that or less than that, we can fold it over back into the first quadrant here of 90 degrees. So let's go ahead and we will have a look at the cosine function. So we have our cosine function here. Our first approximation was just the value of 1. So you can see here that this is approximation here, and it's absolutely perfect at 0 degrees, but it's not very good anywhere else along the cosine function. So the next term was going to be our minus x to the 2 upon 2 factorial. So that's our second approximation here. And then the final approximation was plus x to the 4 upon 4 factorial. So this here is our approximation to the cosine function that we are going to use. And you can see here, again, it's good between 0 and 90 degrees. And again, because of the symmetry of the cosine function, for all our other angles, we can fold those angles into the first quadrant. So let's go ahead now and we will look at the code for the subroutine to generate our cosine function. Now the nice thing about generating the cosine function from the sine function here is that we can use most of the same code. So we have the calling function on the right, the subroutine on the left. Now in the calling function, we're going to now call this cosine. Again, we're going to push a value x onto the stack, and then we're going to jump to that subroutine. So we jump to the subroutine on the left here, it runs through the subroutine, it pops the final value back onto the stack, it pushes the final value onto the stack, and then we return to the calling function and we pop that value off into this memory location called cosine underscore x. So this is in effect just the same as the calling function for the sine, but we're just going and we're going to retrieve the cosine subroutine instead. So let's look at the actual subroutine. So again, all I've done is I've just changed the sine subroutine and I've changed it into the cosine. So in this instance here, we're going to test whether the value 0 has come in. So if it's 0 degrees, rather than going through the whole process of working it out, in that one instant, we will just generate the actual value. So the cos of 0 is 1. So this test for the cos, if the input is 0, if it is, it jumps to 0. So we head down here to 0, and it puts the value of 1 in the output, which is the register R3. Now if the value that comes in isn't the value of 0, then we work through and we generate the Taylor approximation. So the Taylor approximation is the 1 minus x to the 2 upon 2 factorial plus x to the 4 upon 4 factorial. And all of the details in here are pretty much the same. All I've done is changed the constant values. So now we're looking at 1 upon 2 factorial, which is 0.5, and 1 upon 4 factorial, which is 1 upon 24, which is 0.04166. Okay, so it works through and it puts all of the values into register R3, and then we store R3 in cosine, and then we push that value onto the stack, and then we jump to a return address. So we're back up to the calling function, and we pop the value off into our the cosine underscore x address. So that's it's pretty much the same as the sine function. There's not a lot we need to talk about here. So let's go ahead and we will put a value in and just check to see we get the right result. Now we're going to use the angle of 60 degrees as an example. So we can type in cos and 60, and we should get the value of 0.5. Now 0.5 in our fixed point number system is 0080. So that should be the answer we get when we run through the simulation. I have gone and added all of the code into the CPU. So let's go ahead and we will run this here. Now again, it takes about a minute or so for it to run through the entire code. It's a little bit slower because I'm recording this as it runs through, and my CPU is not the newest or the fastest. So that's the simulation finished. Let's go in and we will look at the final result. So the result is here in this box, and it's 007F. Now ideally we would want 0080, but you can see that we are in effect one resolution out from the actual answer. Now this may be in part due to rounding issues, but it's close enough for us, and it's a good approximation to the cosine of 60 degrees. So let's go and we will see the difference between the 7F and 80. So I have run up the little conversion tool here. So hopefully you can see this here. I'm going to type in the value that we should get. So it should be 0080, which is 0.5, but we are getting 007F. And you can see it's 0.496. Okay, so we're getting close to 0.5. It's not exact, and it's probably due partly to rounding issues. Now, we haven't finished with the sine and the cosine functions. There are some other things that we can add in to make it run a lot better. So, for example, I mentioned previously, if we go out with the 90 degrees, then the Taylor approximation is going to get worse and worse. So we really want to stay in between the 0 and 90 degrees. So we want a way of folding all of the other angles back into the 0 to 90 degrees for both the sine and the cosine. So that's something else we're going to have to add into the mix here. But we can see that a simple way of generating the sine and the cosine functions. Now, a much quicker way would be for us to run through a set of results from 0 to 90 degrees and then place those results into memory locations as a lookup table, and then we could simply just go and grab the values that we need. But we're not going to do that for now. We just want to move on and see how we can use the sine and the cosine functions in order to generate some other mathematical functions, and also see how to use the Taylor series to do that as well. So thank you for listening. I'll get you on the next video. Goodbye.